to be here. Thank you for inviting me. It's only my second time in Mexico. I was here 20 years ago doing tourism. And it's good to be back. It's a great city. Thanks a lot for inviting me and having me here. So I'll start, and I'll tell you a little bit about what we do in the lab, in my lab specifically, how we try to understand how the brain works, and how it leads to understanding how the brain works when everything goes well, and how the brain maybe malfunctions and can lead to different disorders. And I will focus today mainly on post-trauma and anxiety and maybe depression. We'll see if we have time. But the main thing will be really how basic science, how we try to understand how this magnificent machine works so well. So I hope it's going to be interesting for all of you. So I said I actually come from mathematics and physics background in my studies, and only later on I understood that actually I want to research the brain because I think it's the most complex system that we have, and in trying to understand the brain we need a multidisciplinary approach, not only biology but actually a lot of computational, mathematical and approaches from physics and engineering. And so that's, from mathematics and physics, I started to learn biology and moved to be an experimental biologist that also uses mathematical tools to try and understand. And so I think one thing that we all know is that the brain is highly complex and can do a lot of things. You mentioned a few, but decision-making and definitely learning and memory, this might be, I think, the two main important functions maybe of the brain. But also, very unfortunately, sometimes, for some reason, our memories can actually, our emotional memories, can actually lead to post-trauma, anxiety, and depression. And actually, the numbers here are presented as a percentage in the US, but that's very similar all across the world. And so if you look at it, the numbers are really huge. And moreover, it's only on the rise. So it's increasing from year to year. Although medicine is obviously progressing and everything, the number of post-trauma, the number of anxiety and depression in the population is increasing, and combining PTSD, anxiety, and depression easily reaches 20% of the population in the US, in the EU. I don't know the numbers for Mexico, but I assume it's not far from it in any way, and it's only increasing. So, and indeed it has been acknowledged in several ways. It's even considered to be kind of the new plague, called the age of anxiety, and in the US a lot of resources are dedicated to trying and ameliorate and help PTSD, anxiety and depression. So one thing I'm sure you all know of is about genetics and maybe the genetic revolution. We now know a lot of the genes that contribute to anxiety and depression, but I think one thing that is highly important to understand is that genetics will never be able to help us completely in solving these issues, because most of the neuropsychiatric conditions, anxiety, PTSD, autism, etc., develop our combination of many genes and develop only later in life. And so genetics will never be completely able to help us solve these problems. And the current approach, and this is really amazing, to treat the neuropsychiatric disorders, anxiety and mood specifically, is basically one family of drugs, which I assume many of you are familiar with. It started with Prozac many years ago. It's SSRI, selective serotonin reuptake inhibitors, and that's the main and only drug basically that has been out there in the last 30 to 40 years. Now, it's a reasonable medication, but unfortunately it helps only part of the population, and it helps only to some extent. And so the problem is that those drugs basically, and again we have only one family of drugs. This is amazing if you think about it. For 30 or 40 years, there's been absolutely no real new discovery in how to treat anxiety and mood disorders. And the main problem is that the approaches we use are simply too crude, too general. These drugs affect one system in the brain, the serotonin neurotransmitter system, and they affect all the brain. And so it's just too general, it's not specific enough, and it lacks specificity. And we need a better approach to target directly how the brain works, to target specific memories or specific anxiety responses. So let's start a little bit to try and dive into the brain, see why is it so complex, how can it generate so beautiful behaviors, but also can lead to this several disorders. And I hope you'll see that we in the lab try to exactly reach the specificity that current medication lacks in targeting these disorders. So if we look and try to understand a little bit how the brain works, then we can kind of use an analog of a city, and the analog basically should be similar to a computer. So we can divide the brain into hardware versus software. And if we think about a city, then hardware will be just the streets and the buildings and all that enables, and the software will be actually people that can communicate with one another. And so in the brain, it's kind of similar. We have nerve cells, neurons, that are all across the brain, and they actually communicate with one another, just like people are. They have their own language, just like we people have. We communicate one another via a language, and neurons do actually the same thing. And nerve cells do the same thing. And so, yeah, just a second. And what is amazing about the brain, and what actually induces its complexity and what enables it to be such a wonderful machine, is the connectivity between neurons. So that's an important point. We have approximately 90 billion neurons, nerve cells in the brain. 90 billion. Now, this is a large number, but actually that's not the important thing, because if you think about today's computers, they can reach those numbers very reasonably. They get to even higher numbers. So 90 billion neurons in the brain is a lot, but that's not the main thing. The main thing is that each neuron, each nerve cell, communicates with 10,000 other neurons simultaneously. So the analogy will be that at each time point, you would listen to 10,000 other people, hear what they say, make a decision what to say to next, and 10,000 other people will hear you say that, and each one of them again listens to 10,000 other people, make a decision, and that's basically how the brain actually works. and how the brain is so complex. So if we try and look again at the analogy of people, we can talk to one person, we can maybe talk, like do a two-people conversation, that's what we usually do. We can do maybe 3, 4 people can talk simultaneously, but we cannot really talk to more than, right? We cannot really have an actual conversation of more than 6, 7 people that talk simultaneously. And in the brain, that is exactly the case. Each neuron talks to 10,000 other neurons simultaneously. And so this simultaneous communication, we can actually call it a high-dimensional pattern of activity, which is basically what makes the brain so complex and how it generates all the beautiful behaviors we have as humans. And that is basically a mathematical problem, because this is literally a high-dimensional space. So let me try and explain this. We know how to think about 2 dimensions. Those are graphs that we know how to look at. We can think about 3 dimensions, right? This is space. Albert Einstein taught us that there are actually 4 dimensions, including time. That's reasonable. But we cannot really imagine what does it mean to do computations in higher dimensions. And the brain is not only does computation in more than 4 dimensions, it does computations in 10,000 dimensions. So imagine that you have, instead of 3 axes, you have 10,000 axes. I mean, we cannot really imagine it, but it's an actual mathematical problem that in each time point, each neuron has an activity pattern that lies in this high-dimensional space, in this 10,000 dimensional space. And this is what allows it to do parallel computations so beautifully. And it's, well, my job, what we do in the lab is try to understand what is the actual language of communication between neurons, but when 10,000 talk to other 10,000 simultaneously in this high dimension space. And the main problem in, yeah, and so it's just showing that. Okay. Now, the main problem in this high-dimensional space is that it obviously allows the beautiful behaviors we have, but when there's some abnormal activity in such a network, in a so connected network, this abnormal activity can propagate to another place in the brain, and I'll show you exactly how it happens in a real example soon. It can propagate to another place and induce abnormal activity in a second place. Now, the main problem is, and this could be underlying some disorder like autism or trauma, etc. The problem is that if we now want to go in and fix this connectivity, the abnormal connectivity we see in a different place can actually achieve different ways to get there, right? Because of the high-dimensional space I just described. Learning on a daily basis from rewards and errors, decision-making, it actually basically underlies our rationale, how we learn on a daily basis and make decisions based on the environment. The other region, which is kind of my favorite region, is the amygdala. It's a rather small brain region, kind of if you go from the eye and from the ear to where the 2 lines meet. And this region is actually highly evolved in humans, and for a good reason. It's small, but still highly evolved in humans, and for a good reason. It underlies almost any kind of emotional response and memory that has. So any learning or memory that is formed under emotional conditions is mediated by activity in this region in the amygdala. And the prefrontal cortex and the amygdala actually communicate, talk to one another. So these are discoveries from the last 15, 20 years or so. They communicate with one another directly, and the balance between them is exactly what determines how do you modulate your emotional responses. So if you you should have a good balance of activity between the amygdala and the prefrontal cortex. So let me give you one example for just from normal learning to PTSD and anxiety. So imagine that you had an unfortunate accident in this place, in this street. The amygdala would be hyperactive every time you go into, you come back to this place, and this would reduce anxiety and stress. Now, in normal conditions, you would, or you should go and see that you can cross the street again and again, and your prefrontal cortex would learn to normalize it, to inhibit the amygdala activity that remembers the accident, and balance it so that you would regain normal behavior and cross the street without so much anxiety and stress. And what happens in PTSD or anxiety is that the prefrontal cortex, for some reason, fails to regulate amygdala activity. And I'll give an example how it happens. So basically, we can see here the prefrontal cortex and the amygdala, and as I said, there's one-to-one connection between the neurons in the prefrontal cortex and those in the amygdala. And when this person comes to the street again after an accident that happened some time ago, the amygdala is overactive and the prefrontal cortex cannot modulate the emotional response. And here you see an analogy, an example in few neurons just to kind of focus on it. So there's activity going from the amygdala to the prefrontal cortex, and activity going from the prefrontal cortex to the amygdala. And the balance between these two activities is what will determine whether their behavioral response will be an emotional stress, anxiety, traumatic response, or a normal, balanced response. So under normal conditions, the prefrontal cortex would, as I said, increase. You see an increased activity going from top to bottom, from the prefrontal cortex to the amygdala, which should regain normal balance and modulate the emotional response. Okay. Another example can be if this person wants to go to a different place, a quiet neighborhood, and let's say he indeed experienced an accident in that place we saw earlier. Now, he goes to a different place, a completely different place, and now the question is, should he be worried about this new road or not? And the answer is, right, he shouldn't be worried about this new road because it's a completely different road in a quiet place. But what happens in post-trauma and anxiety is that he could generalize his response and actually respond as if it is the same place that he was before. Now, this is not a bad thing in general, right? If you think about generalization, which is one of my favorite learning contexts, is that generalization is basically, again, the hallmark of evolution. If there's anything we as humans know to do very well, is to learn in one condition and transfer this learning into different places. So when you all came into the room, I assume you've been in this room before, but let's say you haven't, you immediately saw that chair. It doesn't look like the same chair you know, but you immediately understand this is a chair. You can generalize what you learn in different scenarios to a new scenario very easily. Now, this generalization, which again underlies all of our learning and memory formation, and is so amazing in humans, can actually, when you overgeneralize, lead to applying what you learned in that traumatic event, the accident, in a different place, to a new place that looks not so much similar, but remotely similar. And we actually published a few papers that show that this is indeed a mechanism in post-trauma and anxiety. They overgeneralize the responses, and they now respond to stimuli that are somewhat similar, but not completely similar to the previous response. And it's exactly the same biological mechanism. There should be an activity between the prefrontal cortex and the amygdala that tells the prefrontal cortex should understand that this is a different place and modulate the amygdala activity. Now, the target here and the problem here is that if we now want to modulate the activity between the prefrontal cortex and the amygdala, we need to target the specific memory, right? We need to understand what activity in the brain is exactly the activity that signals the original bad traumatic memory that induces the anxiety, and target only this memory. Because we don't want, obviously, to erase or modulate all your emotional memories and responses. We want to specifically modulate this one memory. And that relates to what I said early on, that current treatments for anxiety and PTSD are simply too general. They do not target a specific memory or behavioral response, but they affect all the brain whatsoever. And we need to actually target a specific memory in the brain and modulate it. So, yeah. And so to do that, we actually need to understand what is the language that the neurons speak. A neuron, we can actually read out the activity of that specific neuron, and you can see here an example. And memory is represented actually kind of as a code in these neurons, between these neurons, and we should now understand what is the code exactly of the traumatic memory and what is the code of a different memory. So this would be the code of an anxiety traumatic memory. This is obviously a very simplified example, and we want to try and understand how do we modulate this memory so that we can make it, I would say, non-traumatic. And the way to do that in the lab is that we really go all the way from behavior and cognitive psychology all the way to measuring the activity of neurons and understanding the code, the language that the neurons actually talk in, which is kind of like understanding, for example, what is the program language of a computer, but only much, much more complex because of this high dimensionality I previously described. And if you would ask me what is my vision, but it's not completely vision because we actually can do this in the lab currently in animal models, and we can do it successfully in animal models, and we're now actually doing it in clinical trials, even in humans, is that we can have a closed loop of modulating brain activity. And this means that we develop specific behavioral models, like, for example, the generalization I explained before. And record the activity, but we need to record the activity of hundreds to thousands, large population of neurons, and to do that we develop specific electrodes that can record the activity of hundreds to thousands of neurons simultaneously. We develop mathematical tools, kind of similar to machine learning and artificial intelligence, techniques that I'm sure you hear a lot about. So we use this to actually read the neural code and understand what is the memory that is now being implemented in the system. And once we identify that this is the memory that is currently in the system, we can manipulate specific brain patterns by modulating brain activity, and there are several methods to do that. So it can be via optogenetics, for example, where with light and viral vectors we can modulate specific activity of neurons, or with electrical activity, like in deep brain stimulation, where we put an electrode and stimulate, but again, we have to first identify that a specific memory occurred in the system, and then we can modulate it, and this will kind of fix the network imbalance, or specifically the imbalance between the amygdala and the prefrontal cortex, but again, only for a specific problematic memory or behavior. And we want to do that, we actually do that in animal models and soon in humans in a closed loop manner. And the reason to do it in a closed loop manner, meaning this goes on fine-tuning until we actually achieve the outcome. It's like tuning hot and cold water. You tune it over several iterations until you get the required outcome, behavioral response per the specific memory. And so, as I said, this almost sounds like science fiction, but it's not. We showed that we can do it in animal models, and we're now doing it actually in patients in different conditions. And yeah, and so I'll kind of finish. No, I'm fine. Yeah, I'm sure. I'm done. And so I think my final words will be that my father always taught me that poor people cannot afford buying a cheap product. He used to say that all the time. We weren't poor, but he said it all the time. Another way to say it is that the longest way around is the shortest way home. And why do I say that? Because at Weizmann, I think the approach, and my lab as well, is that we need a basic science approach to really understand and solve neuropsychiatry. If we try to treat the disease itself, it's not going to work so easy. We have to target, these are two sides of the same coin, basically. How does the brain work in normal conditions under emotional learning, and what happens when it doesn't work properly. If you want to understand one, you have to study the other, and vice versa. You cannot separate them and study only a disease or only normal. You have to study both of them together. And that's what we do, I think, in Weizmann in general. That's kind of the spirit of Weizmann, but in my lab as well. So we develop tools, techniques, and obviously theory and models to understand how the brain works in normal emotional learning and memory formation, and then what happens when there's abnormal learning and memory formation in the network that leads to post-trauma anxiety, etc. I think I'll stop here to give you enough time for questions, and that's it. Thanks a lot.
Muchas gracias. La conferencia, you're not having your, we're thanking you. It was a very interesting lecture. Como ustedes oyeron, el campo que ellos están investigando es un campo súper interesante en donde se está tratando de llegar a aquel recuerdo que es el que genera el malestar, aquel recuerdo que genera toda la conducta errónea o la conducta enferma o la conducta ansiosa, en vez de tratar la enfermedad nada más con un medicamento que puede aliviar a unos cuantos y por tiempo, parcialmente, ¿no? Entonces, no sé si ustedes tienen preguntas, me encantaría que las tuvieran, me encantaría que las compartieran, teniendo aquí un experto en el tema. Entonces, vamos a ir, a ver, 1, 2 y 3, ¿sí?
Thank you so much for your conference. Have you worked this in animal models? I assume you have worked this on animal models with chips. Could you comment anything on that?
Well,
like your chips that you do for closed loop.
right.
I assume you have done the research in either animal models or non-human primates or something.
We do it with rodents, non-human primates, and now we do it with humans as well.
Could you comment
Comment on what?
on your research, on your results, or for, I mean, for lay people, but a little bit about how has it worked?
Oh, so as I said, I mean, so we can actually modulate a specific memory. So the way we do it in animal models is that we first teach them something, an emotional memory, and we also teach them, we actually teach them 2 to 3 different memories, and then we use exactly this approach to understand when do we identify this. So we observe neural activity during learning and memory formation, and then later on we identify when is this memory active in the system and electrically modulate the memory so that, and then we test it a day after or even several days after, and we can see that we can actually inhibit a specific memory without affecting the other memories. And that is basically at the end what we want to do with PTSD, and then there's a delicate point here. We don't want to erase the memory, we just want to down-modulate its emotional response. Now that, I think, is an important thing, especially when we get to humans. We don't want to erase memories, and we can do it.
I have a question. I'm a mathematics teacher. And mathematics causes a lot of anxiety in students.
Oh.
I'm talking about maybe elementary school students. Fractions is a good example.
Yeah.
So they have anxiety, and many times this anxiety is not only learned by a bad experience, maybe they don't understand, but many times it comes from parents.
From what?
Their parents, the father and the mother, who tell them that they also had anxiety with mathematics. So is there any, I mean, you can test the biology of anxiety in learning difficult subjects, but there may also be a component that comes from previous knowledge. Can you comment about that?
So first of all, I'll be careful. I don't think we should stimulate the brain of each student that has some anxiety in school. We should be careful. But I think the answer to the question is mainly an educational answer. That is, we should teach the parents not to do any bias for the kids. But I doubt I mean, it's interesting. Do you think the anxiety you see it obviously harms learning mathematics, but does it really harm their life independently? I'm not sure it's, yeah. But I definitely agree that I think the parents here should be educated better.
Professor Paz, first of all, I want to thank the friends of the Weizmann Institute for this great, wonderful opportunity to be here and listen to this. I'm a cognitive behavioral therapist, as we spoke a bit before, and you really made me think I am a student of David Burns from Stanford, and he, in our cognitive behavioral therapy, we always work with a specific moment, and now I understand why we do it much better. And we always tell our patients, and I think it was maybe intuitively by David, that moment has the same DNA that other moments of anxiety, and if we stumble that one, so I thank you for that, and I'm going to call David tomorrow and tell him, way to go, but I have another comment, and that's that we also did speak before. I see in Israel a lot of use of SSRIs and in the United States, and I see it in Mexico. And I'm not judging anybody, but I wonder if you agree with the statement that the first line of treatment of anxiety should be, or would be, cognitive behavioral systems, other than then going maybe to the next step, because it's too generalized. Yeah. The effect, and also we don't know if it's better than placebo, and also we know that it has some also harmful side effects statistically.
Yeah, so two great questions. I'll say something about both of them actually. I'll start with the second one. And so I completely agree. I think there's over-prescription of SSRI in the US for sure, in Israel as well. I don't know what's the situation in Mexico. And my main objection to SSRI, and again, I don't want to say when it's really required, it's required, but definitely people start with it too early and too soon. And the main problem, as you said, and I said as well, is that it's simply too generic. There's no specificity in its function. It affects the whole brain, one neurotransmitter system. It just cannot be the case that this would help all diseases everywhere. And so I think that in that sense, both behavioral therapy and the biological approach have the specificity to try and approach, I think, a specific kind of anxiety or traumatic event, and SSRI will not. Again, they might, when they're needed, but definitely it should be taken slowly and carefully, and not as the first approach. And as per your first question, I do want to mention something highly interesting that we are working with and has been out there for a few years. So, are you familiar with the term of reconsolidation? Okay, so I think you were referring to that a bit. And reconsolidation is an amazing phenomenon that was discovered a few years ago, and that is that every time you remember and the memory comes back, it actually undergoes again a process of consolidation in the brain. And that means that when the memory is brought up, it can be changed before it is consolidated again. Now this allows both behavioral therapy and biological approaches to revive the memory and then either use behavioral approaches or biological approaches to modulate it again, even if the memory is a traumatic memory from many years ago. And that is something that we use in the lab and we actually see again in animal models and in humans that we can make work. We can make it work so that when the animal or the human remembers the memory, we can modulate it again and have it reconsolidated in a better way, for example, without a traumatic response. Yeah.
I would like to ask you, what kind of equipment do you use to record the signals from the brain and know that the memory is exactly the one that you put it in?
Okay, great question. So there are two approaches using the lab, one in animal models and one in humans. And there are benefits and pros and cons also in humans, I'll say how exactly later on. We use electrodes to record the activity of single neurons in a millisecond resolution. In humans, it's a little bit harder, obviously, to record the activity of single neurons, because you wouldn't take just subjects and implant electrodes, and you would do it in patients, but not when you test in subjects, when you develop the system. So we use fMRI. Are you familiar with fMRI? So fMRI is basically like an MRI. It's an MRI machine, those big magnets, but it's functional MRI, meaning that we actually measure brain activity, or to be more correct, we measure oxygenation, and it's called BOLD, measure level of oxygenation and deoxygenation in the brain, with the assumption that when neurons are active, more blood reaches the region, etc., etc. But without going into details, the main point is that we can identify regions that are active in the human brain in behaving humans. And the benefit is obviously that we can do it non-invasively in behaving humans. The downside is that the temporal and spatial resolution is not yet good enough. So we can record the activity of several millions of neurons in a brain region over millimeter, half a millimeter by half a millimeter approximately, over half a second resolution. So we have less of a resolution, so we cannot really read out the language of the single neurons, but we can still identify activity in regions in the brain. And so we develop them in parallel. It's obviously harder to read the code using fMRI, just because the resolutions are not good enough. It's easier to identify the code of a specific memory with electrodes. But now we actually start to collaborate with neurosurgeons who implant electrodes in epileptic patients and record their brain activity with actually recording the activity of single neurons and identifying memories in humans using this approach. This is really new stuff that we're doing these days.
Well, first of all, I want to congratulate you for all the work you are doing. I am a psychotherapist also, and I wanted to ask you, have you, I suppose because you see patients, that maybe some patients have had some treatment before they get to you. So I wanted to know if you find any difference between patients that have not had treatment or patients that they have had.
Well, it's a good question, but I have to say that I'm not a psychiatrist and I don't treat the patients per se. So we look at the patients in terms of. So we actually try, so that we have a controlled experiment. We try to take patients that either were treatment-free or with treatment, but all the same conditions. So it's a good question. Interestingly, the psychiatrist, like one of them I collaborate with, started asking this exact question, and he's now testing it in his clinic in the psychiatric hospital we collaborate with. He thinks that the treatment they use indeed helped to, for example, for the generalization in what I showed. But to answer if we can better modulate brain activity in patients that underwent treatment or not, it's still too early for me to say.
It's a hope what you are doing.
Yeah, exactly.
Thank you.
Are you
Yeah, me.
Hi.
Hi. I would like to ask if you have any scientific information about how meditation works in neurological brain functions.
There are a few recent studies about meditation, mainly using fMRI. I mean, I don't want to comment about how meditation helps anxiety and stress, because I think there are people in the audience that even connect to that better than I can, because I mean, it's the field of psychology and psychotherapy, and I'm a brain scientist there per se. And there have been some studies with fMRI that have looked at the brain of people that do meditation on a regular basis. People who do not. And there's some evidence that they can indeed regulate their activity, that the activity renormalizes. But it's hard to say, I mean, it's hard to identify specific differences, convincing differences between, and it also depends on the specific scientific question you're asking. If the question is meditation beneficial for anxiety and stress, I would say, I'm not the expert, but probably yes. If you're asking, does it modulate brain activity, I would say it has to modulate brain activity, because obviously meditation does something. And I think it needs to be asked in a more specific way. What is the question about meditation that...
If it really make changes in neurological interconnections, or you have found anything, or it is a scientific way to demonstrate this?
Long-term effects, I'm not aware of any evidence that show long-term effects of meditation in neurobiology findings. Short-term effects in the fMRI, yes, there are effects. I mean, it changes brain activity under meditation. But if there are really long-term neurobiological effects, this is still an open question. I'm not saying there isn't, I'm just saying it's an open question. We don't yet know the answer. And that's something that unfortunately we cannot study in animal models. So, yeah.
I want to ask you something. Going back to the beginning of your talk, you were comparing the thousands of neuronal connections with the dozens, if so, of human connections. Do you think it is possible that in the near future, the connections that are now starting to grow in Facebook, Instagram, and all those programs could upgrade to the same number as the neuronal connections? And what would be the effect?
Well, it's a very interesting question, and so we collaborate actually. So there are a lot of computer science research that looks at social networks, right? And we actually collaborate with them because the approaches, the mathematical approaches, are actually very similar. So what they try to do is try and identify what are the hubs of activity in this large dimension. So if you look at Facebook's, it's also a high-dimensional network. Not as high as the brain, because there's still no 10,000 connections to 10,000, and also the temporal resolution is much, much lower in social network versus in the brain. But the mathematical methods are very similar. It's a dimensionality reduction techniques to look at to identify patterns of activity in social networks, just like in the brain. Now, if really social networks are going to get to the complexity of the brain, I don't see how any time in the near future it's really it's going to get to that level, but I don't know.
I recently read a book by Robert Sapolsky called Behavior. Maybe you've heard about it. Sure. The book is very complex, but it makes a lot of, it's very broad, but it makes a lot of stress in the fact that the environment is the one that actually is ruling out how genes activate, and therefore substances hormones are, activated, created, and then all interaction between the different areas. So in your talk, you didn't mention anything about the environment, the influence of the environment, and particularly in your research. And so I don't know if you can explain a little bit more about it.
I actually think that that's exactly what we do. I mean, it depends obviously how you define environment, but that is exactly what we look at. So when I say learning is the environment, right? You undergo this or that emotional effects, and they accumulate in your brain as memories. And so, what is an environment if not going on and learning different things? So, for example, if you had not you, sorry, I don't want to, but if someone had an unfortunate bad childhood and not so supportive parents, this is, I guess, what you would mean by environment. But for me, as a boring scientist, I would say these are different, cumulative learning effects, that emotional learning incidents that accumulate into an imbalance in the biological network. So that is exactly what you call environment is, I think, what I call learning models and trying to cognitive learning models and trying to take the environment and I would say formulate exactly what in the environment led to malformation of memories. Is that okay?
Two more questions?
Yes, here. Hi.
Hi. You finally got the microphone.
Yes. I relate myself to the person who asked about meditation somehow. But I wonder particularly if in your work or in the Institute have been considered to investigate the effects of relaxation techniques, meditation, all this breathing and all that, in not just like it changes the brain, like can it be a tool as powerful as a medication, or it's been considered to do that in a research in a proper way?
So I'll answer straightforward. I'm sure these techniques can help. This is not the research. There's no psychology department at the Institute. We are a brain science department. So if a student would come to me and ask, what are the effects of these on the brain activity, just as well as before, I would be happy to investigate what is actually happens in the brain that underlies benefits from these behaviors. But in terms of purely cognitive research, how does these techniques help behavior? This is not something, that there are other departments that look at that, but not in the neurobiology department. That's basically what I'm saying. Okay?
One more question.
Hi, my question is, I understand when you talk about the memory, the specific memory in post-traumatic stress disorder, but when you talk about anxiety, I think there are a lot of patterns there. There is not a specific one. So my question is, do you go for all of the patterns that are relate, or do you go for one that you think is the root, and the other ones like modulate, just secondary to that?
So that's a kind of question that would make me say, how about you come and do a PhD in my lab? Because it's a great question, and I think that's one of the projects we're currently dealing with. And we compare that again, both in animal models and humans. That's an open question in psychiatry. You know, there's a lot of comorbidity between PTSD, anxiety, etc. And so one of the options we look at the lab is whether multiple learning events, it's called insults in biology, lead to a more generalized anxiety instead of PTSD, and or can lead to depression in different sense. And my response would, the first response, and we looked at the differences and we published a few papers about it, is that in generalized anxiety, which is basically what you would call anxiety, GED is just a more classical name, and what usually happens is that there are several events that were cumulative, and if they were spread enough and not focused on one topic, then it will lead to more general anxiety, and I would say a more spread and non-specific imbalance between the amygdala and the prefrontal cortex. So it wouldn't be, as you suggested, tied to one memory or two memories, but it would be more general. And so the question is, and that's what I come into a PhD, is whether do you want to target the 4 or 5 memories that you identify as being more anxious, or do you want to modulate the activity in general and not specific to a specific memory? Now, whether the first approach or the second approach would be best for anxiety is one of the questions we look at now, and I would hypothesize that it would be very patient dependent. And that's why the closed loop is, by the way, also, in my view, the only way to go, because if you have a closed loop system, you can actually see that, okay, this was not enough, let's now do the other one, etc., etc. It's a good question.
Bueno, pues nos da mucho gusto que hayan ustedes podido preguntar y acercarse un poco más a las investigaciones del Dr. Paz, y les agradecemos mucho su presencia. Un aplauso al doctor, porque realmente con él podemos ver cómo el Weizmann está con tecnología de punta hacia problemas súper importantes del ser humano. Buenas noches, nos vemos la próxima.